Righty, hello year 11. So we're doing 2.3 and 2.4 today, and then this is your last video. Anything for this term. Last video for this term. Anything after this is just going to be revision for your test and working on your D&Ds. So, on page 141 of your textbooks, blue box is the stuff that you absolutely have to know in your textbooks. So for this 2.3 circuit analysis, what you need to know is circuit analysis and the circuit design involve calculation of the potential differences across the current in and the power supply to components in series, parallel, and composite circuits. How to solve problems using those two equations. One is volts, the other one is for resistance, and the potential difference is equal across each parallel component. So solving problems and using IT equals I1 plus I2 all the way up to I to the n and 1 over RT. We'll get to that. Alright, so first and foremost, circuit diagrams. You have to know how to draw them. Okay? So on page 141, down the bottom, there is a lovely diagram for you there. It's not very clear. It basically has the symbols for the power and battery supply, what a wire looks like, what the resistor looks like, how you draw a light bulb, a junction, a switch, all that. You need to know how to draw them. You will be drawing them in your tests and your assignments. We have an assignment on electric currents later. So yes, you do need to know how to draw them. Alright, so first off, we have Kirchhoff's law. So what does he say? Kirchhoff's law expresses charge conservation, the junction law, and energy conservation, the loop law, in a closed circuit. So on page 142, the second paragraph there, it says, in general, a junction is any point in a circuit where three or more wires meet. Kirchhoff's junction law states that the current entering any junction in a circuit must equal the current leaving that junction. If that were not the case, charge would either build up or disappear from a circuit. As an example, consider the circuit shown in figure 2.44, which is right next door to it. At point A, three wires join to form a junction. In this example, the current entering the junction is I1. It is equal to the sum of the currents leaving the junctions, I2 plus I3. Okay. Alright. We went through electric potential energy, which is the change in electric potential, should equal to 0. Since the change in volts equals work divided by charge, which is equivalent to the change in potential energy divided by charge, blah, 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 blah. Okay, let's look at how to actually apply Kirchhoff's law. So page 143, I have an example 2.08. So, what do we have? We have a 100 milliamp current flows into a junction at A in the circuit below. Calculate the current I2 if the current I3 is 60 milliamps. So, I1, say the charge that we have, equals to 100 milliamps, right? Charge 3, so I2 is unknown, and I3 is equivalent to 60 milliamps. Okay, so we have information there. I1 is 100 milliamps, I2 we don't know, and I3 is 60 milliamps. So we rearrange this equation to find I2. So instead of having I1 equals I2 plus I3, we have I2 equals I1 minus I3. Okay, so this here is our original equation. We rearrange to find I2, and we get this instead. Okay, what does that equal? I2 equals 100 minus 60, which equals 40 milliamps. That's it. It's not that hard. It's very easy. Okay, that's all that is. So that's when you're giving 2 amp, excuse me, 2 amp units. 2 amp measurements. Okay. Oh well, we have example 2.09. A 70 milliamp current flows around a loop in a circuit below. First part, calculate the potential difference in the resistor R2 if the potential difference across R1 is 90 volts and the potential difference of the power supply is 15 volts. Okay. So first we need to calculate the potential difference for R2. So we are using our change in volt equation, which is delta V is equivalent to delta V1, delta VT, delta V1 plus delta V2. Okay? These are triangles next to the V. Okay, so delta VT is equivalent to delta V1 plus delta V2. Okay? Delta VT is change in voltage total. We know what that is. We're trying to find the voltage for one of them. So that becomes delta V, what did I have there? 2 is equivalent to the change in volts total minus the change in volts in the first one. So our VT is equivalent to potential difference of the power supply is 15 volts. So that's a maximum. Our total is 15 volts. And our charge for V2, our other supply, is 9 volts. Okay. So if we write that out on the side here, I skipped a step, sorry. We have delta VT is 15. Why is it so blurry? And then delta V1 is 9 volts, and delta V2, we don't know. That's meant to be a question mark. I know it doesn't look like one. Alright, so delta V2 equals 15 minus 9, which equals 4 volts. Sorry, 6 volts. Wow. It's been a day. 6 volts. Okay. Once again, not difficult math. Math you all know how to do. You can absolutely do it. Alright, so now we have our volts. We can now calculate the resistance. So resistance is capital R. Okay. And the formula that we use, so a formula that uses both voltage, charge, and resistance is delta V is equivalent to IR. So volts are equal to charge times resistance. Okay. Alright, now we need to find the resistance, so we rearrange the equation. It becomes resistance equals charge over change in voltage. Okay. So this is our original equation. We rearrange it to get the resistance on the other side. That is an I, not a 1. Okay. And I've wrote it the wrong way around. Yeah, I wrote it the wrong way around. Okay, note to self, don't do YouTube videos this late at night. Okay, now we have our information from the previous equation that we did plus the question. So, you know, our voltage is 6 from what we just did, and the question before it said a 70 milliamp. So we know what our I charge is. And my writing is getting worse as time progresses. Equals 6, and charge equals 0.7 times 10 to the negative 3. Cool. So resistance equals to 6 divided by, well, not 7, 70 times 10 to the negative 3, which equals 0.68, whoops, equals 0.86 ohms. Okay, remember, resistance is measured in ohms. Ohms is given by omega, and then 0.86. We divide it together. Okay, that's all. You have these formulas on your formula sheet, so don't freak out if you don't remember them. They are literally given to you. Okay? Alrighty. So next, looking at resistors in series. So you're like, Miss, what does that mean? It means that this is in series. They go one after the other, around through. Okay, so the circuit goes around, and they are in series, so the first is 1, then 2, then 3, and just loops through. This here is in parallel, where it goes through all three resistors at once and before making a loop back to the beginning charge. Alright, now, the formula for resistors in theory is T or total or equal to is R1 plus R2 plus R3 all the way up to Rn. Okay, Rn is however many numbers or things you have of, wow, how many resistors do you have in theory? However many that may be. Okay, so in example 2.10, circuit consists of 3 resistors connected in series to a 240-volt battery. And the current circuit is 46.6 microamps. The first resistor is 225 ohms, and the second resistor is 155 ohms. Calculate the resistance of R3. Cool. Okay. So, your resistance total that it can equal to is, so RT is the largest amount of volts a battery can have divided by how many amps are currently in the system. So for this equation here, we have a 24-volt battery divided by 46.6 times 10 to the negative 3. Okay? This is our RT or R total or R equal to, whatever, however they want to label it. Basically, the maximum resistance that can be had is equal to the amount of maximum volts divided by the amount of amps currently running through the circuit. Okay, so our R3 is equal to our RT or R equal minus R1 minus R2, which equals the 24 over 46.6 times 10 to the negative 3 minus, what was our first ohm, 225 ohms minus 155 ohms. And that equals to, after you plugged everything into a calculator and you've done the work hang out, it equals 135 ohms. Okay? So, we have our initial formula, RT there. We found what our RT value is. We rearranged the formula, so we're finding R3. So that's RT minus R1 minus R2. RT minus R1 minus R2 equals that. Okay, so that's how much resistance R3 has. Right, now we can calculate the potential difference across it. So that is basically finding how many volts are passing through R3. So for that we do change in voltage is equal to the current that is running through times by the resistance that's being had. It's being had. So our change in voltage is unknown. Now the current that's going through is what's in the system already. So the current circuit is 46.6 microamps. So that's 46.6 times 10 to the negative 3 times it by our resistance, which we just worked out, which is 135, and that equals to 6.29 volts. Okay, that's it. Done. So those are for resistors in series. If we are doing it in parallel, we are dividing 1 by the number of resistors that we have. Sorry, it's 1 over the resistor for every resistor that we have. That made minimal sense. Okay, so going to page 145 and looking at, again, it is blurry and I apologize for that. For this here, so we have 1 divided by the total amount of resistance that a circuit can have equals to 1 divided by resistance 1, 1 divided by resistance 2 plus 1 divided by resistance 3. Yeah, because they're working in parallel. They're gonna all go through together. Okay. So to use that, looking at example 2.11. So a circuit consists of three resistors, R1, R2, and R3, and they gives you the value, and it tells you it's connected in parallel. Calculate the equivalent resistance in the circuits. So that is 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, is 1 over 2 to 5 plus 1 over 1, 5, 5 plus 1 over 1, 3, 5, which is equivalent to 0.0183 ohms to the negative 1. Okay, so with this, once you've calculated this out and you have this, you're not done yet, because this is 1 divided by RQ is equal to that. So for this here, you need to divide 1 by this number here. So RT is equal to 1 over 0.0183. And that is equal to 54.6 ohms. Okay, that is your final answer. Not this here, where you have a number, but it's equal to 1 divided by RT. You need to divide 1 by that number there to get what your RT value actually is. Okay? Please make sure you finish that equation when you do it in your practice tests. Alright. Cool. Then what? Alright. So, combination circuits. Combination circuit is a circuit that has parallel components and what's the word? Series components together in one circuit. So when you do equations with that, you have to break it up into parts, as it shows on page 146. So replace parallel resistors, replace series resistors, find equivalent resistance. There's a few steps to go through that. Okay. 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 So when it comes to combination circuits, if you're given something that's really complicated, you should be able to, so you say you're given, so like example, like figure 2.49, they've broken down the circuit into parts. So there's 2 resistors in series and 2 in parallel. They've merged the 2 in parallel together and they've given the value R divided by 2. Okay? And now then you have 3 resistors in series, and they simplified that again and made it into 1 resistor, and they've done 2.5 times R. Okay? Add the 2 together, add the half together, you get 2.5. So, okay. Next, 147 talks about ammeters and voltmeters. Oh. Wow. The thing they use to measure volts. And how to connect them in a series. In a circuit. So with a voltmeter, you have to put it on either side of a resistance so you can actually measure voltage going in and voltage going out, depending on which way the electric current is flowing. and an ammeter can be put in between the power source and the resistor, as shown in the diagrams. Alright, and then questions. Alright, page 154. That's run electrical power now, 2.4. What do you know? So power is the rate at which energy is transformed by an electrical circuit. Wow. Power is the rate at which energy is transformed by a circuit component. Solve problems involving power equals change in energy divided by time, and power equals charge times by change in voltage, and the use of Ohm's law formula. Solve problems involving the cost of electricity using kilowatt hours. Solve problems involving efficiency equals use of energy divided by total energy times 100, or efficiency is power output over power input times 100. Cool. All right. Let's go to our formula. We're looking at power. So our formula for this is power is equal to the change in electric potential energy divided by time equals work divided by time. So I'm not going to break that down for you. It's in your book, page 154. This right here. Okay? No, actually we'll write it out. Okay, so power is equivalent to change in potential energy divided by time is equivalent to work done divided by time, where P is power, and it's a capital P, not a lowercase p. A lowercase p is momentum, and delta EP is change in potential energy. GW is work, and T is time. Alright, as per usual, funnily enough, power, the unit for power is work, energy is joules, work done is also in joules, and time is in seconds. Okay, oh sorry, not work, watts. Power is given in watts, make sure it's a capital W. Electric energy and work are both given in joules, and time is always in seconds. Okay, so standing unit of power, the watt is named the Scottish inventor who found it, and it is defined as 1 joule per second. Alright. Alright, so example 2.12, determine the power output of a microwave that transforms 51 kilojoules of energy in 30 seconds. Alright, cool. So, if something is in kilojoules, make sure it is the number times by 10 to the power of 3, because it's not just a joule, it is a kilojoule, that is 1,000 joules. Okay. So, we are finding the power, so power is equivalent to change in energy over time. So our kilojoules is 51 times 10 to the 3 divided by 30, which is equivalent to 1700 watts. That's it. Best thing about electric circuits is that the math is simple. Okay. So suppose an amount of charge Q moves through the battery at a time t. The charge's potential energy will increase by change in charge. Change in potential energy, which equals the charge times by the change in energy, change in volts, right? Blah, 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 blah. So we have a second formula for power, which power is equal to charge times by the change in voltage. Okay. Power equals charge times by change in voltage. Okay. So to use that, we have the example 2.13. So a 1.5 volt battery supplies a current of 0.16 amps to a light bulb in an electric circuit. Calculate the electrical power of the light bulb. Easy. Power equals charge times change in volt. Power, so our charge is 0.16. Our voltage, our change in voltage is 1.5. So power is equal to 0.16 times 1.5, and that equals to 0.24 watts. This down here. That's it. That's it. Alright, example 2.14, you find the power of a resistor. So, ohms, go for that. So, power is equivalent to the charge squared times by R for the resistance. Our charge is given to us as 4, and our resistance is 75. So power is equal to 4 squared times 75, which equals 1200 watts. Then 2.15, a 24-volt battery is connected to a 1090 ohm resistor. Calculate the output of the resistor. Okay, we've got a bit of a different formula for this. We have power is equivalent to the change in volts divided by the resistance. Okay, our change in voltage is 24, and our resistance is 1090 volts. Alright, so 24 divided by 1090 is, 24 squared, sorry, which is equal to 0.53. Wow. Volts. So these formulas that we are using come from earlier in the book. Where exactly I'm trying to find. It's work done. We've been to that. Okay, electric current formula. So that's on page 116. From all the way back there is where we're getting these formula from. We're rearranging this past ones that we want. Alright, next, energy use. So, energy consumption is measured in kilowatt hours. It is possible to interconvert between joules and kilowatt hours using the conversion factor below. So 1 kilowatt hour equals 3.6 times 10 to the 6 joules. Okay? 1 kilowatt hour, 3.6 times 10 to the 6 joules. So to go from kilowatts per hour to joules, you divide, kilowatts to joules, you times by 3.6 times 10 to the 6. To go from joules to kilowatts, you divide by 3.6 times 10 to the 6. Yes, that is a conversion you are going to have to memorize. You do not get that on your cheat sheet, I'm pretty sure. Alright, so example 2.18 looks at how to do that. Alright, so a 4.4 kilowatt oven cooks a roast meal in 30 minutes. Calculate the cost of cooking the meal. The energy provided charges 41.5 cents per kilowatt. Alright, so first thing we need to do, we need to find out how much energy is being generated. Okay, so our energy is equivalent to our power times by time. So our change in energy. How much energy are we actually using? So our power is equivalent to 4.4 times 10 to the 3 because it is kilowatts. Remember, everything starting with a kilo is 10 to the power of 3. And our time is equal to 30 minutes, which is 30 times 60 seconds. No, I'm not going to time that out. I think it's 1200. Yes. Alright, so that equals 4.4 times 10 to the 3 times by 1200 equals 7.9 times 10 to the 6 joules. Cool. Alright, now we have, so remember, energy is in joules. We have our joules amount. Now we need to convert from joules into watts. For that, we divide by 3.6 times 10 to the 6. Okay, she goes 7.9 times 10 to the 6 divided by 3.6 times 10 to the 6, which is equivalent to 2.2 kilowatts per hour. Okay, so this is what that looks like. Change in energy is equivalent to power times by time. Our power is 4.4 times 10 to the 3 watts, and our time is 30 times 60 seconds. We plug all that information in and we get our final answer in kilowatts. Alright, so now we know how much energy we're actually using. Next question, how much are we paying? So cost is equivalent to change in energy times by cost divided by energy. Okay, because that's what it's given us. It charged 41.5 cents by energy given. So we do, drawing a little box down here. So cost is equivalent to change in energy times by cost over change in energy, okay, which equals 2.2 times 0.415. Okay, you may ask where the 0.415 came from. It is because he's charging 41.5 cents per kilowatt. So we divide 4.15 times 1,000 to find out how much 1 watt would cost, which is 0.415. Then we times the two together, and that equates to $0.91. There, that one there. Alright, last bit, energy efficiency. That's it, page 157, and then we're done. So, efficient energy, or percentage of efficient energy, is useful energy divided by total energy times by 100, because it is a percentage. Okay, or efficiency can be found by output divided by input times by 100, gives you a percentage. So, for example, 2.17, we have an incandescent light bulb emits 40 joules of energy for every 120 joules of input energy. Calculate the percentage of efficiency. Calculate the efficiency. Alright, so the useful energy, it uses 40 joules. So, alright. Useful equals 40 joules. Total equals 1,200 joules. Okay. Percentage is a question mark. Our efficiency percentage is a question mark. Alright, so we do 40 divided by 1,200 times 100 equals 3.3%. So incandescent light bulbs are not very efficient at all. They only use 3.3% of power that's given to them. In this case, anyway. That's it. That's how you do that. Same thing with example 2.18. 60 watt light emitting an LED. Sorry, a 60 watt LED has an output power of 24 watts. Calculate the efficiency of time. So, efficiency of time? Efficiency of the LED. So, percentage efficient equals question mark. Out is 24. That's not 24, Lenny. Out is 24 and input is 60. Okay. Percentage of efficiency equals output divided by input times by 100. That's 40%. Okay. That's it. That's all it is. And that concludes your learning for this term. Alright. Do not forget to work on your D&Ds and do not hesitate to ask questions. Please and thank you. That is all. Fare thee well. Goodbye.